Welcome back. Now, as we know, Designer is a complete drag and drop interface designed for almost no coding. So the first thing in almost all the cases is to get the data for our pipeline. And let's say we want to use this automobile price data for our pipeline. So you can simply move your cursor on this and click on Use Dataset, and it will be added on our canvas. Then another way of doing that is simply clicking on it, hold it, and drag and drop it on the canvas. Alright, so once you have your own dataset, it will be visible here under the datasets, and you can do the same with it. Now all the assets over here will be in the form of a rectangular processing box. So let's try to understand what characteristics each of these boxes will have, and let's do that in a little bit more detail. Now because this is a dataset, and if you click on it, it will show you these parameters, outputs, and so on, depending upon the type of asset it is. The dataset asset or this object can only provide the data. Remember, it's not processing the data. It is just the container of the data. And that's why you only see this output node over here. And through this node, our data will be provided for further data processing. This designer also provides this search box using which we can search for an asset. So let's say I want to search for one data transformation asset called as select columns. And immediately you will be provided with that module or asset. And don't worry about what this module does at this particular stage. We will go through all the minute details of these modules as we progress through the course. But at this moment, what I want to show you is how the dataset and processing modules are structured. Now, as you can see, this select columns modules has the nodes on top side as well as the bottom side of it. The one on the top is used for accepting the input. So it can take this dataset as an input and then perform column selection as part of its processing. And for that to happen, for taking this as an input or accepting this as an input, all we need to do is connect the output node of this dataset to the input node of this select columns module. And that will mean this module can now use this dataset. Alright, it's very similar to flowcharts. And once this connection is made, you can just move these boxes anywhere and it will still retain the connection. Then you will also see various parameters of this module on the right hand side. You will have to click on this module to get that. And we can change them and get the kind of processing we want from this particular module. I hope it is making sense. And I'm deliberately going a bit slow because there are some very handy and useful operational tips for working with the designer. Now, as we saw when we clicked on the dataset, we got this information sort of thing about it. But for this select columns module, you not only see this parameter, but you also see these output settings, run settings, comments, as well as the module information. Now, because this select columns does some data processing and creates an output, we need to store that intermediate output as well as need some compute resources to do that processing. And that's why we have the output settings for this module as well, apart from the default output settings that we had in the settings. I'm sure you remember we understood the default settings in the previous lecture. And those will of course be applied to all the module, but we can override those from these individual settings. So by default, the output will be stored in our default data store that gets created when we created the workspace. But if you want to store it in your own data store, you can override that by clicking on this second radio button and then specifying the details of it. Similarly, every pipeline will have some default compute target as well. But for some reason, if you want to use some different compute machines for certain steps, you can do that here. So the reasons can be many. You may want to use higher memory for some operations, maybe higher CPU or even a GPU machine for some algorithms. And that you can change and override right from this place. Then comment is for simply adding the comments. Then the module information provides this link of learn more. And let me right click on it and open it in a new tab. And on this page, if you go there, you will see the detailed description of this module with all the parameters, the input required, as well as the output of that module, and various other details of how to use it, and so on. From exam perspective and getting the detailed information and knowledge, I strongly suggest that you go through these descriptions at least once. You will see this entire library under the module references, and it's a good read for getting the in-depth understanding of Azure ML. Alright, and let me go back to the designer. Great, and I hope that is a good enough overview of the designer. So we saw how to open a designer pipeline. We also saw the default settings for it. Then we understood these different elements of the canvas editor. We also saw how to search a module, how to bring them on the canvas, how to override the default settings for output and run, and how to get the information for the module. Now, getting the dataset by creating it first over here and then dragging it on the canvas is one simple method of making the data available for our pipeline. Now, there are some more ways of doing the data I/O or data input-output, such as creating the data manually, importing it from a data store or from a URL, as well as exporting it to some blob storage through the data store. So let's try to understand them in a bit more detail in the next few lectures. As always, it's a pleasure to teach you. Thank you so much for watching and have a great time. Welcome back. In this lecture, we are going to learn how to import the data that resides outside our AzureML workspace using the AzureML Designer. And as you can see, I have already created this workspace and also launched the studio. So first, click on this Start Now button of Designer. Then click on this plus button to create a pipeline. And because every workable application that we create is created by first creating its pipeline. So if you have just created this workspace and not created the compute instance, it will always show you these settings page saying there is no compute instances found. But I have a compute instance created, so I'm going to select that. And let me also rename this pipeline as import data pipeline. Great. And now to use the module, you can simply search for it here and type import. And there you have this import module. Simply drag and drop it on the canvas. All right. And now if you click or highlight any module, it will show all the parameters that it requires in this frame over here. So for the import data module, we have this data source as the first parameter. And it has got these two options of using a data store or using the URL via HTTP. Now we have seen how to get the data to our workspace using the data store. So for data store, import module becomes just one more place. And if you select that, it will ask you to choose the data store in this second drop down. You can select whichever is available or you have created. And if you want to create a new one, you can click on this link to create a new data store. And then in this box, you can provide all the details for the new data store. We have done this earlier and it is very similar. So I'm going to ignore it for now. And here I'm going to select this default workspace blob store. And once you do that, this additional parameter for the path will be required. You can click on the browse path, and if you have any files available there, it will show you that. As I mentioned earlier, this is a kind of duplicated effort, and I just wanted to show you the flow over here. So for now, let's just see how to import the data using URL via HTTP. Okay. So for that, let me select this as an option under the data source, and now it will ask for the data source URL. Now, in order to show this from a real URL, let me go to a new tab. And there, let me search for adult income UCI. And hit enter and click on the first link of UCI. So the UCI, or University of California at Irvine, has created a huge repository of various datasets that we can use for practice purpose. And within that, we have this adult income prediction dataset. For now, I'm not going to go through the details of this dataset. And we will see that later on when we will do some more stuff with it, some more prediction and some more data manipulation with it. For now, let's just go to the data folder. And here it will show you this index of parent directory, index, adult.data, and so on. Our data is a part of this URL of adult.data. And if you click on it, depending upon your browser settings, either it will open the data in a new tab or it will ask you to save the file as the .data file. You can save it if you want to, and to open it, you can use Notepad or any text editor. And you'll require it just in case you want to compare it with AzureML import module and its result. And let me copy the URL. So right click on it and then copy link address. Great. And let me now come back to the designer pipeline and paste this URL in this text box. And once you do that, it will start accessing it and will start validating the URL as well as get its schema, which is nothing but the column names, column types, and so on. So give it a few seconds and it should be done. And once it is validated, you can click on preview schema. And as you can see, it will show you various columns which are available. And now, because our data does not have column names, it has by default given these names starting from column 1 all the way up to column 15. It has also provided the data type of each of these columns. And for now, it's just a string and integer. And also, if you want, you can select or deselect any of these columns. I'm going to select all of these except the path. Then you also have this parsing option, and if you click on it, it will allow you to edit how you want to parse the data. As part of initial validations and checks, it has chosen these options of delimited with comma as a delimiter and so on. And if you already know the data schema and want to change these options, you can do it right over here. For now, I'm going to discard it because I know the data and this schema is very much in line. And then also cancel this schema preview just to avoid any changes that I may have done accidentally. Okay. But remember, we have still not imported the data. What we have just done is simply validating the data and its schema. And the actual import will happen when we run this import module. And to import this data or to run it, we need to simply submit this pipeline. So click on it. And now every pipeline is part of an experiment. And it will ask you in this dialog box to select or create a new experiment. For now, I'm going to create a new one and give some name to it as data pre-processing. Remember, it can only take letters, numbers, underscore, and dash. So let everything else to be its default values, and I'm going to click on Submit button. It's going to take some time, maybe a few minutes, because it is going to load a lot of modules, a lot of packages, and so on. And now, as I mentioned earlier, if you have the credit from Azure, you can simply create the compute instance and let it run while you work with me. But if you're on a paid account, I suggest you first create these pipelines, save them, and later on in one go, you can run them one after another. All right. So while it is running, I'm going to pause the video here and come back once it is done. Great. It is completed with this green line. Means our pipeline run was successful. So now simply right click on this module and click on preview data and then the output data. Wow. And as you can see, we now have imported the data with these 32,000 records and 15 columns. And let me maximize it by simply clicking here. And there you go. You can visualize your data right over here. It does not show all the 32,000 records here. It just shows 100 records as part of the data preview. You can visualize the data if you want to. And if you have downloaded the data file, you can go ahead and compare it as well. For now, I'm going to end this lecture here. And let's see a few more things related to data processing in the next one. As always, thank you so much for watching. Welcome back. In the previous lecture, we imported the data using this import data module. And let me quickly visualize it for you. And as you can see, and as we know, we do not have the column names for this data set. So in this lecture, let's add that. So let me close these views and come back to the designer authoring page. Okay. And now the module to add the column names as well as do various other metadata operations is called as, and let me search it here as edit space metadata. And there we have it. So simply drag and drop it on the canvas. Great. And now in order to run this module after this import data, we simply need to connect this output node of the import data to the input node of the edit metadata module. And now if you click on this module, you will see various parameters that it requires as usual. So first is the columns, which is the list of columns on which we want to apply some changes. For now, those changes are nothing but the change of column names. And to select the columns, simply click on this link of edit column, and it will provide you this dialog box where you can select the columns in various different ways. So you can select them either by rules or by names. So rules simply means either some of the columns using their names or column indices starting from 1, or if you select column types, you can select them based on the type of data they hold, such as Boolean, string, integer, and so on. So if you select the string data type, all the string type columns will be automatically selected. Then you can select all the columns or features, labels, or scores. Now you must be wondering, what's the difference here? Usually we use these two terms of columns and features in one breath. But Azure makes a very clear distinction among these 4 types of columns that we have. And very soon in some of the future lectures, we will see that. Okay? For now, before we proceed further, let me just show you what happens when we select this radio button of by name. And as you can see, we see a very familiar UI where we can select or remove the column names from this side to the selection side. So you can simply click on this plus button to add columns, or this minus button to remove them from this side. Or you can use the add all or remove all to either add or remove all of them. Pretty simple. And for now, because we need to change all the column names, I'm going to select all of these columns and add all. Okay, and save it. Great. For now, let's park these three things of data type, categorical, and fields, and we will come back to them in the future lectures. Let's first provide the new column names in this text box, and they need to be provided separated by a comma. So let me go back to the adult income dataset on the UCI website. Now, if you scroll down a bit, you will see this attribute information, and below that, these column names starting with age, working class, and so on. There are in total 14 column names here, and the 15th one is the income. So let's go back to the designer, and in order to save some time, let me pause the video here and come back after I'm done typing these column names. Great. And I'm done over here, and as you can see, I have simply provided the column names separated by comma over here. And you can simply go back to the UCI website and simply copy and paste them one by one, or type them one by one. And we are now ready to submit this pipeline. So click on this button, and I'm going to use the same data pre-processing experiment and leave everything else to their default values, and then click on submit. And it will now submit this pipeline. And once again, we will have to wait until it is finished. And as I mentioned earlier, this could take a couple of minutes or maybe more. So let me pause the video here and come back once it is done. Wow, it is done now, and it is completed means successful. So once again, to see the output, right click on the edit metadata, preview the data, and then results dataset. And there you have it. And now let me maximize it. And these columns now make much more sense. And you can go through it if you are done. For now, I'm going to close this output. Now, some of you who are familiar with Python and Pandas must be wondering it's a long process compared to the functions in Pandas. But remember, we are learning a completely new graphical way of doing things using these boxes for modules and connecting them using these dots. And more than that, this edit metadata is a very powerful module and has multiple functionalities within it. And you will see that very soon. Then another point I would like to mention is we are seeing this edit column functionality for the first time. And I had to explain it in detail. And as you will see in the next few lectures, this functionality is very common to most of the other modules, and I won't explain it again over there. So when you actually do it, you will not spend that much time. And even the future lectures will be a bit shorter when we deal with edit columns compared to these initial ones. Great. And that also brings us to the end of this lecture. And let's see these other functionalities of edit metadata in the next lecture. As always, thank you so much for watching and have a great time. Welcome back. And now that we have run this pipeline successfully, let's get the brief overview of this pipeline menu. And for that, click on this pipelines menu. And here you will see the pipeline runs, which will show all the different runs, or basically every time you submitted the pipeline, it created a run, which is what you see here as a list. And if you want to provide some meaningful name to it, you can do that by editing this display name. Then under the pipeline data points, you will be able to see any endpoints that you created. So loosely speaking, endpoints are nothing but the final output of your training experiment, which we then deploy as a web service that you can consume in your other programs. And we will see that in future when we deal with it. Then under the pipeline draft, you will see various pipelines that you have created so far. Then click on this one, and it will open the import data pipeline that we have created. All right. So that's more or less about how to navigate through this pipelines menu. Great. Now let me go to the experiments menu. And remember, when we submitted our pipeline, it was part of an experiment. So here you will see any such experiment that you have created. And apart from that, you can see the latest run as well as some of these details. So let me click on this experiment. And inside that, you will see the stats for various runs or pipelines that you ran under this experiment. So things like how many of these runs completed successfully, how many are running, how many failed, and so on. If you want, you can explore this menu on your own, and I don't think you will face any issues in understanding it. For now, I'm simply going to click on this run one so that we can see the output of it. Now, as you can see, there is huge amount of information that is provided over here. And I'm going to cover that in the subsequent lectures when the time is right and when we would be generating the data for some of these menus. For now, I just want to show you where to look for any error that you may get. For that, you can simply go to output plus logs, and here you will see the execution logs as well as the standard error and standard output logs. Alright, now when we use this designer interface for creating pipelines, it's very unlikely to make an error. Generally, I use this when we use the AzureML SDK. And even this error message you can see in the designer itself if there is any error while executing. So let me go back to the pipeline draft. And here, similar to this completed message, if there is any error, it will say failed and also show a brief message of why it failed, which if required, you can debug. And most of the frequently occurring ones can also be found under the module information on the Azure documentation page. And I'm sure you know how to go there. Great. And with that overview covered, let's now proceed with the remaining data processing tasks. Now, if you are planning to take a long break, I suggest you delete all your Azure resources by going to the Azure portal and then clicking on all the resources and then deleting the resource group itself. Otherwise, you may end up paying unnecessarily. Great. With that, let me end this lecture here, and as I always say, it's a pleasure to teach you. Thank you so much for watching. Welcome back. So we have created this pipeline earlier and run it successfully. Now to see the output again, let me simply go to this edit metadata and click on preview data and click on results dataset. And let me maximize it. And now if we click on these columns, you will see that age is of type numeric. Then we have the work class as a string type of feature, which is fine. I mean, that's what the data is. So when you import the data, majority of the time, this is what you will see. So either the data type is numeric or string. But we may want to convert these into different data types, such as maybe categorical for this work class, or maybe Boolean for the yes and no type of variables. Because it's very much possible that the data may not always be in the same form that you want. So now for this work class, we have 9 unique values. And such features need to be called, or I would rather say we need to convert them into categorical features. I hope you remember the lecture on understanding the data types during the basics of machine learning. Now, many algorithms actually expect such string variables to be converted into categorical features before we can actually run or train them or train those algorithms. So simply string here could be a problem. Okay, so for changing this, we may need another edit metadata module. So come back to the designer canvas and let me type or let's search and then drag and drop another edit metadata box. And now connect the output of this first one to the input of the second module. Click on edit columns. And this time I'm going to select the columns by rules instead of the name. So in this drop down, let me select the column type. And then in this drop down, you will see all the data types or column types. So let me select the string type of columns and then save it. Now here, you will not see the column names in this box. But if you click again on this edit column and then select this radio button by name, you will see all the string type columns which are selected for this transformation. Now, I have just taken the string type of columns, but there could be certain numeric variables which you may still want to convert into categorical. So just do not take it literally that all the string has to be converted into categorical. There could be certain numeric variables as well. All right, great. Now, one more point. Remember, this selection is only for the data transformation, and the output will still have all the other columns along with these ones. Only thing that is happening here is the other numeric columns will remain as it is. Okay, so let me cancel it for now because it is already saved. And now here under the data type, you see unchanged as well as all the other data types. Now we do not want to change the base data type. And what I mean by that is we have these columns as string and we only want to change them to categorical. Now only when you wanted to change the base data type from, let's say, numeric or any other original data type to string, then we would have selected string or any other column or data type. So whatever we select here will be the new data type. But for now, I'm going to keep it unchanged because we have already selected the string. I hope I'm making sense here. Now, for changing the category of the data, which is what we want to do, we select from this category drop-down this value of categorical. So that means it will be a string variable with a category as categorical. Great. Now, fields also, I'm going to keep it as unchanged, and there is no need to add any column names as we have already done that. So everything looks good, and we are now ready to submit this pipeline. So click on the submit button and let it run for some time. I'm going to pause the video here while it is running, and then we'll be back very quickly. Great, it is indeed completed, and now let me go to this second edit metadata, right click on it, preview the data, and then the result dataset. And let me maximize it. So we still have the same data, there is no change absolutely. And now, when you see this age column, it is of type numeric, whereas the work class will now be of type categorical. Remember, and I'm repeating it multiple times, the base data type is still string. It is just the feature type category is now categorical. Okay? And like this, you can explore all the other columns, and you should see them in the same order. So this is how we can use the edit metadata to change the data type as well as changing the category of the data. But it has certain limitations. I mean, the edit metadata module has certain limitations that you can only do one transformation at a time using this module. So if you need to do multiple transformations, you require multiple instances of this module. Okay? And as I keep mentioning, for more details, please go to the module information. And here you will see all the details of this module. And as you can see, it's a very comprehensive module, and we will use it in future lectures as well. So go through it, and it will also help you in increasing your knowledge of Azure ML and also to pass the DP100 exam. Great. And with that, we have come to the end of this lecture. As always, thank you so much for joining me here, and have fun. Welcome back. So we are still doing the data input output, and so far we have just used this one data transformation module. And now that we have seen how to import the data from the external source or even from the blob store, let's now see how to export the data to the blob store. Because it is very much possible that after doing some data processing right over here, you may need to store the data at let's say some other Azure storage account to maybe a blob storage. So for storing the data directly from the workspace to some blob storage, we need the export data module. So let me search for it and then drag and drop it on the canvas. Now, as you can see, it requires an input, but it does not produce an output as it does not have this output node. That is because its output is actually exported data to some other storage. Okay. Now, let's say you want to store the data with only some of the columns after providing these column names as part of this edit metadata module. So to do that column selection, we can use another module called as, and let me search it here, as select space columns, and there it is. Let me simply drag it here, and now let me make some space by hiding this menu and bring this thing in center. Great. Now this module takes another dataset as input. So I'm going to connect the output of this first edit metadata to the input of select columns in dataset. So basically, we can connect this one output to multiple modules. And that way we can get some sort of parallel processing done over here. So you can keep doing, for example, data processing, and in the meantime, the export can happen. So export can go on parallelly to another blob or whatever storage, and some other processing that we will see later on can happen parallelly. So let me select a few columns from this select columns by clicking on this edit column button and select by name. And now let me add all the columns here. And then just in case you want to verify, I'm going to remove just one column of education num from this selected ones. Education num is basically same as education. It's just some number assigned to the type of education. For now, we are simply understanding these modules, so don't worry about what these columns stand for. And if you want, you can play around here. I mean, you can remove few or maybe add this education num, whichever columns that you want to keep. And then save this. And I'm going to keep rest of the settings for select columns to their default values. And now let me connect the output of the select columns module to the export data module. So we are going to export the resultant dataset from this select columns module. Now the question is where it is going to export. Well, that is what we need to provide using the parameters of this module. So as you know, everything happens in and out of the workspace using the data store. And that's why we see these options of type of data store and the actual data store configuration. Now let me go to my data store list. And as you can see, I have already created a data store using a blob storage and this storage account. And if you have not kept yours already, then I suggest you create an Azure storage account and then the blob container within it, and pause the video in case you are doing it along with me. And also make sure that you create the data store using that blob storage. Okay, now let's go back to the designer. So I'm going to select the data store type as Azure Blob Storage. And then if you click on this drop down, it's going to show all the data stores of type blob storage listed over here. So let me select this JK blob. And now this new text box will appear that requires the path. Now, if you take your mouse to this information symbol, you will see that it says it requires a relative path. And what that means is you don't have to specify the storage account.azure.blob name and all those cryptic and long URL. You simply need to provide the directory and the file name relative to the blob container. So what I'm saying is it will simply add that path using the data store. So it will simply add the original or the absolute path using the data store and then export our file. Okay. And the reason I'm saying file is because that is what is required as a bare minimum. All right. And still, I would say that won't be a good way of storing it directly the file name inside the blob storage. So let me provide some folder as and let me call it test folder for now. Okay. And followed by a slash and then the file name as adult income as one word .csv. All right. I hope you are still with me. Then next, we also need to provide the file format as either CSV, TSV or the Parquet. Now, you may wonder that if we are providing the file extension here, then what is the need to provide the file format? Well, the output, and listen to this, the output of the select columns is not in the CSV format. It is in the default dataset format of Azure ML. And the export module will not recognize it just by the file name that it is a CSV file. So when we specify the file format, the export module will first convert the data in the CSV or TSV or Parquet format, and then it is going to export it by that file name. Now, just so that you know, I'm not cheating. Okay, let me go to the blob storage and let me hit the refresh button here, and it will show it as empty. Make sure. So I don't have any file or folder over here. Okay, so let's go back to the designer and then run our pipeline and see whether it exports the data as we want it. So let me simply submit this and then keep the experiment names, etc. and all the default settings as it is. So in this case, it is not going to run all the steps once again, unless we change their parameters or we change the sequence or anything like that. So it's only going to run these steps which are not completed. And let it run for a couple of minutes, and I'm going to pause the video right here. So the couple of minutes went in a flash for you, thanks to the video editing. And it's now completed here. And let me go to the storage account and then to the blob storage. And let me just refresh it. And there you go. We now see this test folder right over here. Click on it. And wow, we now have our adultincome.csv file created right over here. Let me click on it. And you will see all the metadata for this file under the overview. But I'm not much interested in that. So let's see if we can edit and see the output. So click on this edit. Now there is a problem here. To edit the file inside this Azure portal interface, as on the date of recording of this video, there is a limit of 2 megabytes. And because this file size is more than 3 MB, we won't be able to see it here. And if you have been doing it with me, what you can do is download the file using this download link and then save it in your local machine. And then you can verify whether the file has been written correctly or not. And I'm pretty sure it is correct if you have followed me all along. Great. So in the last few lectures, we have seen how to import the data from a URL, then how to do some basic data transformations using edit metadata, as well as how to select columns or chop the data vertically, And finally, how to export the dataset in different formats using this export data module. Great. And in the next few lectures, let's see some more data transformations before we start the machine learning modules. As always, thanks for watching and have fun. Welcome back. And today, let's see how we can merge the two datasets vertically. And by vertically, I mean we can create a combined dataset using two independent datasets. So if I have to give an example, and let's say we have these two datasets with one having these 4 columns and the other with these 3, then when we merge it, we simply create a combined dataset with 7 columns. All right. So let's go to the designer and see how we can do that. And now I have already uploaded the 2 CSV files called AC1 and AC2 to the workspace and registered them as datasets. And you can get these files from the resources attached to this lecture. So let me first drag and drop the AC1 and then the AC2 as well. Great. And let's first preview the data of AC1. And it's a very simple and small dataset, nothing to worry as such. And when you maximize this, you will see that this dataset has 8 columns and 23 rows. Now, column names are pretty self-explanatory. We have some basic employee data of name, age, department, gender, and so on. Let me close this and let's now preview the AC2. Now, this one has 3 columns and once again 23 rows. And our job is to combine these two files and create a dataset with 11 columns and 23 rows. So let me close this. And now it's very much possible in real life that the kind of data we need for machine learning, it may be produced in different systems and we may need to create a combined dataset for final algorithm training. And that's where we need to make use of, and let me search it here as add columns, and there it is, drag it. And as you can see, it has these 2 input nodes, which simply means it takes 2 datasets as input and then produces the combined one at this output node. And good thing is it does not have any parameter as such. So let me connect the AC1 to this first or the left node and AC2 to the second one. That's it. And that also means we can only combine 2 datasets at a time. And if we need to combine 3 or more, then we have to repeat these steps. Okay. And now let's submit this pipeline and see what we get. So you can create either a new experiment or use an existing one and then submit it again. Now it will start running. So let me pause the video here and come back once it is done. It's completed. So let me right click on it and then preview the combined dataset. Great. And as you can see, now we have this combined dataset with 23 rows and 11 columns. And you can go to the right and verify that the columns have been added. Great. And here I also want to make one more point. And that is if your right hand side dataset has lesser records than the left one, then it will add the NaN or the null values to all those rows. And it does it in a sequential manner and not based on an index or anything like that. And another thing is you don't have the option to select certain columns while adding them. So you may have to use the select columns module either before or after the add columns module and then get the desired output. Great. And with that, we have come to the end of this lecture. And as always, thanks for watching. Welcome back. And now today we are going to learn how to add rows to the dataset. So again, this is a concatenation of data, but in this case, the number of columns in both the datasets are same, but the rows are different. So I have these 2 datasets called AR1 and AR2, and you can once again download them from the resources, then create and register them. We have done that multiple times by now, so you should not face any problems there. So let me drag and drop them on the canvas first. All right. And first, let me preview the data for the AR1. And as you can see, it has got 8 rows and 11 columns of name, age, and so on. So let me close this and now let me preview the AR2. Once again, it has got 11 columns and the 17 rows, which are different from the earlier AR1. Okay. Now, there are a couple of things you have to make sure before you can concatenate or merge these 2 datasets. First is the name and number of columns in both the datasets have to be same. So we have 11 columns and their names are also same in both these data sets. So that is taken care of. Then the second point is the data type. So for every column, the data type of that column in both the data sets should be same. I mean, you can't have this last working day as a string in one column and a date or boolean or numeric in another. They have to match the column by column. Alright? Otherwise, you will surely get an error. Great. So let me come back to the designer and let me search and add the module of add rows and drop it on the canvas. And now let's connect the AR1 to the first node and AR2 to the second. Once again, as it happens with add columns, this one also takes just 2 data sets as input. And if you have to merge more than one, you may have to repeat this particular step. Alright? So for now, that's all that we need. And let me now submit this pipeline. So I'm going to use the same experiment names. If you are doing it for the first time, you can create a new one and then submit the run. As usual, I'm going to pause the video and come back when it is done. It has run successfully, and now let me open the output of the add rows and see what we have there. There you go. It indeed has the 25 rows and 11 columns as we expected. Also, if you go down a little bit, you will see the data for Will, George, Adam added after the first 8 rows. Great, and with that, I hope now you can add the rows for any dataset of equal columns. As always, thanks for watching and have a great time. Hello and welcome. Now in this lecture, we are going to learn about the normalization of the data. We will see what is normalization, why we need to normalize the data, what are the benefits of normalization. Alright? So let's begin by understanding what is normalization. Well, it simply means adjusting the values on different scales to a common scale. Okay? So let's say we have temperatures recorded for these 4 cities over here. And it has been given in the degree Fahrenheit. We have also recorded the temperature of London, Paris, Delhi and Tokyo, but they are recorded in degrees Celsius here. And let's say if we want to combine these, we may have to either bring all of them on the Fahrenheit scale or convert all into degrees Celsius and then merge them. So basically what we are doing is kind of normalization or bringing them on one scale. And now read this definition again and it will make much more sense now. So as I said earlier, it is adjusting the values on different scale to a common scale. Alright? And I hope that explains what is normalization in the simplest possible term. Now, the next question that you may have is why we should care or why should we normalize it? Can we not handle the data as it is? Well, let's say we are trying to build some sort of a regression model. And this is how it will look like in a 2-dimensional space. And let's say the equation of the line is, or the equation of the line that has been derived is given by this formula, which is y equal to a plus bx1 plus cx2 and so on. And let's assume that x1 is the loan term or time within which the applicant will repay the loan, and x2 is the salary that he or she will earn. Now listen to this very carefully. Now the value of the loan term can vary from maybe 12 to 120 or even 240 months if the person has taken the loan for 20 years. But the salary can take any value. It can be few thousands of dollars to even few millions. Now what that means is the salary as a variable will have much more influence on this equation. Even slightest change in the coefficient of this salary will result in a much larger change due to the higher value of x2 or the salary. And it's completely under the influence of one variable only. I mean to say the value of y or the prediction that we want to make will be under the influence of just salary. And that's why it is very, very important to bring them on one scale. Apart from that, many algorithms in machine learning, such as clustering or even principal component analysis, rely on the Euclidean distance, or what we know as the distance between 2 points. And even the optimization of neural network require these values to be normalized. And that's why it is in our interest to normalize them before we apply any algorithm or start processing them any further. Okay? So once again, let's define it in statistical terms. We are basically standardizing the variables, and usually we want them in one range or one scale. So all the data points of any column or features as they are called will be on one single scale. Okay, I hope I'm making sense. And that one scale can be between 0 and 1, or in case of z-score transformation, the data will be normalized or spread in such a manner that all the columns will have the standard deviation of 1. So while they can be on different scale, after the transformation, all of them need to be on just one scale. I mean, all the columns that you're trying to normalize. I mean, it won't make any sense that we keep one of the features on a scale of 0 to 1 and the other on -1 to 1. That is not normalization. All right. And last but not the least is we can apply it only on the numerical columns. I mean, it's common sense and it's very obvious that we can convert some values to another using mathematical means only if they are numeric. Okay, great. So then let's see what are some of the most commonly used normalization methods. The first, and it is also the most popular method, is the z-score transformation. And it's also called as the standardization method. And it is calculated as the x value of the record, okay, minus the mean of the x or the mean of that particular column divided by the standard deviation of that particular column. So basically, the data can vary from any negative value to any positive value, but the transformed data will always be with a standard deviation of 1. All right. Then the next one is the min-max normalization method. And in this, we subtract the minimum value from the x value or the input value and then divide this whole thing by the range or the difference of the maximum of that column and the minimum value of that particular column. Okay. And I'm sure by now you must have realized that for the minimum value, the numerator will be 0 and for the max, it will be same as the denominator. And that's why this will transform the data on a scale of 0 to 1. Great. And another way of transformation is by taking the exponential of x and then putting that in this formula. Now that brings us to the end of this lecture on normalization. So in this lecture, we saw what is normalization, why we need it, and the normalization or transformation methods for normalizing the data. And in the next one, let's do it using Designer. And I'm so glad to have you in the class. See you in the next one very soon. I'm just a second away. Welcome back, and let's now see how to normalize the data using the Azure ML Designer. For that, I have already created and registered the adult income dataset. If you want, you can also use the import module and import this data from the URL of the UCI. All right, so bring it on the canvas and then let me once again preview the data. Now, as you can see, we have some of these fields such as age, which goes from minimum of 17 to maximum of 90. At the same time, the final weight is from 19,000 all the way up to 1.2 million. And surely they are not on the same scale. I mean, it's common sense. Even the other numerical columns such as this capital gain, capital loss, as well as hours per week are on a different scale. So as we said, let's normalize them and let me close this. So the module to normalize the data goes by the same name as normalize with a Z. Drag and drop it on the canvas. And let's connect this dataset to the input node of the normalize data module. And now let's see the parameters required by this module. So the first is the transformation method. So currently it supports these 5 methods of z-score, min-max, logistic, log-normal, and tanh. So we saw the formula for z-score, min-max, and logistic. You can always do some reading about the other 2 also. But for now, I'm going to select the min-max, which will basically convert the data on a scale of 0 to 1. Okay. Then the next parameter decides how we should treat the constant values in a column. Remember, if we select all the numeric columns by the column type, then it is very much possible that we may end up selecting a column which has just one value for all the rows. So there is no minimum or maximum value, just one constant across the entire column. Now, in such cases, when we keep this parameter value to true, it will simply convert those constants to 0. I hope I'm making sense over here. Then, as usual, we also need to select the columns that we want to transform. So click on this edit column link, then select the columns by type and then all the numeric columns. Okay, and save it. Great. And with that, we are now ready to submit this pipeline and then submit or run to an experiment. So submit it and let it run for a couple of minutes, and I will be back in a flash once it is completed. And there you go. We are now done. The run is completed, means it was successful. So let me now preview the data and then go to the transformed dataset. And once you maximize it, and then if you click on any of these numeric columns, you will see all the values between 0 and 1. So the new minimum value is 0 and the new maximum value will be 1. And that will be true for all the numeric columns. I hope it is now clear how the normalization of all the numeric column has taken place using this min-max normalizer. Great. And now let me come back to the designer and let's now see one more transformation method of z-score. So let me simply change this transformation method from min-max to z-score and then submit the pipeline. And I'm simply doing this just to show you how different transformation methods work and what kind of scale we get from the data. So let me pause the video while it runs. Great, it is completed, and as usual, right-click, preview the data, and then the transform dataset. And here, if you click on age, you will see the minimum and maximum values are different. But this entire column now has a standard deviation of just 1. And if you see the other columns, you will notice that even though their minimum and maximum are different than age or other columns, but their standard deviation is also always 1. So basically, the z-score brings the data to a scale with standard deviation as 1, whereas the min-max transformation will bring in the data on a scale between 0 and 1. Alright? And I hope that is clear. So let me go back to the designer. And now, both the times when we right-clicked and went to preview the data, we saw this transformation function getting generated. And you may wonder what exactly is that, and why it is creating this function, and where it is used. Well, allow me to explain it with this same example. Now, if you remember, for this column of age, the minimum value was 17 and maximum was 90. And this is the basis on which all the transformations have been done for this column. Similarly, for the final weight, the minimum was 19302 and max was 1.226 million. Now, remember, this transformed data will then be given to a machine learning algorithm which will then train itself. And after everything is done, we will deploy this entire model with all these steps as a web service in production. And there, the data may or may not be in a batch. There, if we get just one record with one value of age, how are we supposed to transform it? And for that purpose, we create this transformation function with the minimum and the maximum values stored in it. So if we are using the min-max function, the formula inside may look something like this. The only unknown here is the x, which is the input to the web service later on in the production. So this function then substitutes the value of x and proceeds further with the transformed value. And similarly, for the z-score method, the transformation function will store the standard deviation and other details and make sure that the only unknown is the value x, which then it will calculate during the production run. I hope by now, with the last couple of lectures, it is now clear what is normalization, what are its different methods, how the transformed data looks like, as well as the significance of the transformation function. And I hope I could make it interesting and simple enough for you. It's always a pleasure to teach you. And with that, please allow me to end this lecture here. Have a great time. Welcome back, and today we are going to learn how to deal with the missing values. And for that, I have this employee dataset already created. Let me drag and drop it on the canvas. And let's now preview the data and check the details of it. So under this profile, you will be able to see some summary statistics of each of these columns. And let me sort it on this missing value count. So now you can see that the column of age, marital status, as well as education and gender have missing values. And we have to deal with them because when we feed this data to the machine learning algorithm, it won't understand the missing data at all. Because remember, the ML algorithm can only deal with numbers. So it simply cannot understand or it won't know what to do when the data is missing. So close the data preview and let's bring in another module of Designer known as the clean missing data. Search for it and then drag and drop it on the canvas. Alright. And then as always, connect the dataset to the input node of this module. And now let's see various parameters required by this module. So the first is of course the columns that we want to clean. No issues there. And then comes these minimum and maximum missing value ratios. This can be a bit confusing, so please allow me to explain them in detail. Now, missing value ratio is the ratio of missing values and the total values in that column. We will talk about the minimum and maximum of that little later, but let's just understand a very simple definition of missing value ratio. So if a column has 100 values and 10 are missing, we will say that the missing value ratio is 0.1. Simple. Now, using this minimum and maximum missing value ratio, we provide the conditions under which the missing values will be cleaned. So, for example, if we specify the minimum ratio as 0.2 and our column has less than 20% of the values as missing values, then no cleaning operation will be performed. So, our age column in this employee dataset has 3 missing values and the total values are 25. So, the ratio of missing values is 0.12. Now, this ratio has to fall between the minimum and maximum missing value ratios that we specify if we need to do any cleaning operation. So, if we specify 0 and 1.0, it will be cleaned. It simply means clean the column even if one missing value is present. But if we specify minimum as 0.2, then it won't do any data cleaning. Similarly, if the maximum is less than 0.12, again, there won't be any data cleaning. I hope it is clear. Then this parameter of cleaning mode specifies the mathematical method or function using which we want to replace the missing values. So it can be your own custom value, it can be mean, median, mode, or if you want, you can remove the entire row or entire column that has even if there is one missing value. Okay? And now remember, whatever method we choose here will be applied on all the columns that we select as part of this columns to be cleaned parameter. So what that means is this cleaning method will have to be compatible with the data type of the column. So basically, if we choose cleaning method as mean, median, then we cannot choose any non-numerical columns here because we cannot calculate its mean, and then it will surely give you an error. It also means that we need to perform multiple operations of this module if we need to clean numeric and non-numeric columns. Alright? Then next is the generate missing value indicator column. Now, if we set this to true, it will add an additional binary column to our dataset with true and false values. So if it is true, which means the value of that row has been replaced using some sort of cleaning method. Okay? And finally, if a particular column has all the values missing, then there is no point in having that column and we can choose to remove it. Okay? So I hope all the parameters are clear for now. So let me click on this edit columns link and then choose the column types and within that all the numeric columns and save it. Then I'm going to keep the minimum missing value ratio to 0, which means even if one missing value is present, perform the cleaning operation. Then max as 1, which means entire column has missing values, which kind of doesn't make sense if you know what I mean. But for now, I'm just going ahead with it. Then the cleaning mode as replace with mean, missing value indicator as true, and remove the columns with all the missing values. Great. And now let me simply submit this pipeline. And I'm going to use the same previous experiment over here and then submit it again. So give it a minute or so and it should be done. And I'm going to pause the video for now and come back when it is completed. It is completed, so preview the data and then the cleaned dataset. So now our dataset has 5 additional columns. So if you remember, it earlier has 11 columns, but now it shows 16 over here. And give me a second and I will explain that. But for now, let me scroll down a bit here. And wow, here we see this value of age as 34.812, which is nothing but the mean of this column and is a replaced value. I mean, it was pretty easy here considering everything was integer except these 3 values. But there is another way of finding it. And let me go to the right, scroll to the right. And now you will see this additional column of age is missing with the values as true or false. So we see a true value here and maybe a couple of more. So if you click on that column, you will see it has 3 values for true and rest are all false. If you check other numeric columns, they didn't have any missing values. And that's why this is missing indicator column had only 1 value of false over there. And I hope you know why these columns were added. Basically, it's because we had the generate missing value indicator column set to true. And now that explains how to use the clean missing data module. But here we saw only the numeric columns. Now, as a part of the exercise, I want you to add another clean missing data module. But this time, take the output of this first one as input and then perform the cleaning operation for the string columns using replacement method as mode. Okay, for now, please allow me to end this lecture here and have fun performing the exercise. Thanks for watching. Hello and welcome. And now in this lecture, let's see another important step in data processing. And it is known as splitting the data in training and test set. You may have seen or heard of it at many places. So let's understand that with a small example. And for that, let's go back to the school. The teacher here is teaching some arithmetic operation and let's say some multiplication. And she provides certain example and also tells the kids how to do it, as well as what is the answer for the examples that she has given. Now, after a few weeks, there is the time of exam, and if the teacher asks exact same questions to the kids, they will definitely have some good score, because they have already seen those questions and most probably know the answer. But how do we know if the kids have really learned it? Well, then the teacher usually won't give the same questions. She will ask a different set of questions by changing the numbers. So now, if the students have understood the concepts, they will answer it correctly and get good grades. We can say that's a high result from the tests or high test accuracy. Whereas if the students get not so good grades in the test, we say it was a bad test or low test accuracy. So when we get a high test accuracy, we can say that the training has been good. And when we get the low scores in the tests, we should first question the training that has been imparted, assuming the student studied. And it is the same with the data. So when we have the full data set, we simply break it down into training and test data set, so that we can train our algorithm using the training data and then test that learning using the test data. That way, we will come to know whether our kid, which is the algorithm over here, has been trained enough or not. Then sometimes we divide the training set into different beans, also known as folds. And consider this as those daily or weekly tests which are not graded, but they provide a good feedback on how much we have learned and in which areas we are weak. And then based on that, we can fine-tune the training. And it's the same over here. We will also see this kind of partitioning in some other lecture. But for now, please allow me to explain another important concept in data split known as stratification. So let's assume we have this data set with 10 rows and it has got 6 yes values and 4 no's. So now when we do a 40% split without stratification, it is possible that we may get all 60% of the training data set as yes and all the test data set as no's. Now, even though the selection is random and the possibility is very low, we still have a possibility of that. The probability of this happening increases if the no's are much lesser percentage, say just 5 or maybe 10%. The biggest danger of such a split is that our algorithm will never be trained on identifying the no's. It can result in giving completely wrong results. Then another possibility is that we may get all yes in the test set. Now, in this situation, even though our algorithm is trained to identify the yes as well as no, there is no way to test whether it has been trained to identify no. We would be simply assuming that it has learned. That is also not a good situation. Now, there is always a higher chance of getting both the yes and no's in both the dataset. But the proportion of yes and no in this dataset may not be same. Now, look at this split which has stratification on this column. And when we do the split at 50%, what it is doing is it first calculates the number of records as per that percentage and then adds it to the test or train. So when we select split as 50%, each of these dataset will have 3 yes and 2 no's. If it was a 25% of test, then we would have 1 record of no in the test and rest in train. I hope that explains what is stratify as a parameter. It's an important concept and I always recommend that we should use stratification when we are dealing with classification type of problem. Great. For now, that's all we have in this lecture, and let's do the data split in the Azure ML Designer in the next lecture. As always, thank you so much for joining me here. Welcome back, and let's now see how we can split the data using the designer. And for this, I have created a sample of the adult income dataset. And as part of that sample, I have simply taken first 100 records from the CSV file and created a new dataset for this experiment. It simply makes the counting of the records much more simple. So drag and drop it here. And then the module for splitting the data into train and test dataset is also known as, and let me search it as split data. There we go. And again, bring it on the canvas. And now connect the dataset with the module input node. And let's now see the parameter it requires. So first one is the splitting mode or the splitting method. Here we can either split them by rows, which will be then picked up randomly, or you can also choose the regular or relative expression. So you can use regular expression in case you want certain rows with values starting with certain letter or number in the first dataset and rest of them going to the second one. Remember, this split data module generates only 2 output datasets. Okay? And then we can also use the relative expression if we want values as a relational expression of equals to, less than, greater than, and so on. So these are usually some additional functionalities, I would say, that Microsoft has provided for the split data module. But as you will see, majority of the time, we will use the split rows mode for creating the training and test dataset. So select that. Then the next parameter is the fraction of rows that we want in the first dataset. And it can range from 0 to 1. So 0.5 here simply means 50% of the records will go in the first output dataset. And just to check it, and because we usually use a larger percentage of data in the training dataset, I'm going to use 0.7 over here. Okay? Then the next parameter is whether to select the rows at random or they should be selected sequentially. So let that be true. And that basically means we are going to select the rows randomly. And because of that, we also need to specify the random seed. Now understand one thing. Because the records are picked up randomly, and if we rerun the experiment, there is a possibility that every time we run it, different records are selected for the 2 output dataset. Okay? And if you are using some machine learning algorithm and it gets a different training set every time, it is also possible that we may get different output. Okay? And for that purpose, we need to provide a number here as a random seed so that even if we run the entire experiment multiple times, we will get the same records in both the datasets as long as other parameters are not changing. I hope I'm making sense here. And as part of this random seed, you can specify any number, 0, 1, 2, 3, 9, 8, 7, or any other number that you like. 0 is not mandatory or 1, 2, 3 is not mandatory. You can specify any number. Then comes the stratified split. And based on the previous lecture, we know what that means. So select that as a true and then specify the column on which we want the stratification done. So in this dataset, we are trying to predict whether the income level of the person is more than 50,000 or not. So typically, you will use the stratification on some predicted variable or the column. And majority of the time, this is done in case of classification. So let me click on this edit column. And here, provide the name of the column, which in our case is income. Save it. And that basically completes the configuration of this module. And I hope you have followed me all along. And even if you have few doubts here, they will be absolutely clear once we run this pipeline and then see the results. So to see the results, what are you waiting for? Hit this submit button and make sure you have the compute instance created and used as the default compute target for this experiment. Then use the existing experiment or create a new one and then submit it again. Let it run for a couple of minutes. Great, it has completed for me. And now, before we see the result dataset, let me preview the data once again for the adult income dataset or this sample. So right click and preview the data. Then in the profile, go all the way down to the income column information. And now here you will see that there are 75 rows with income less than or equal to $50,000. And 25 are those records where the income is more than 50,000. So 75 and 25 is the proportion. Make a note of those numbers. Okay, close it. And let's now right click on the split data module, preview the data and see the first result dataset. Now, out of the total 100 records, we have 70 records in this first dataset. And that is because we specified the fraction of rows going to the first dataset as 0.7. Okay. Then click on the income column. And now you will see that it has got 52 rows with value less than 50,000 and 18 rows with value greater than 50,000. And the reason for that is because we specified the stratification as true. So the 70% of the 75 records, and you can do the math, will be 52.5. Now it cannot break one record and put half of that in every dataset. So it basically rounded it off to 52. And that's why we see 52 values here. In the same manner, the 70% of 25 is 17.5 and it rounded it off to 18 records. Great. And I hope with this you have understood how the split data module works. But to get better hand on it, I strongly suggest you to try different combinations of these parameters. and also try the regular and relative expressions on some of these columns. And then you can compare the rows, how they were split, how the records moved in one data set versus another. Okay? And in the interest of time, for now, I would like to end this lecture here. And let's see a few more interesting things as we go along. As always, thanks for watching and have fun. Hello and welcome. And today we are going to build our first machine learning model using logistic regression. So let's first understand what is the logistic regression. Well, this is one of the most simple yet very powerful classification algorithm that is used to predict the probability of an outcome. The outcome can be binary, such as yes or no, such as will this customer buy my product, or multiple outcomes, such as what will be the quality of wine, will it be low grade, high, or average. It's a supervised learning method that basically means we must provide a dataset that already contains the outcomes to train the model. So let's now see what does logistic regression mean and how it works. Well, before we start building the model, let's first try to understand how the equation for the logistic regression can be derived. Now, as you know, a simple regression may have an equation as y equal to b0 plus b1x. Let's take an example of a number of claims versus the age of the insured. Also, let's say we get an equation such as number of claims equals to 18 plus b1 times age. And that gives us a line that passes through these points. And if we get a new data point with age value, we can predict the number of claims using this regression line. The line can take any shape and form depending upon the equation. But what if the data is not as we expected and the question we are trying to answer has only two possible outcomes, such as will this customer buy my product, yes or no? And now, if we draw a straight line like this, it will not give us the correct result. Now, there are two issues with this line. First, what about the data points on this line over here, which are assumed as continuous features? And secondly, because of the continuous nature of it, it can take any value, whereas our output has only two values. Okay? So let's take a step back and ask ourselves, what's the question? Well, the question is, what is the probability that this customer will buy? We may not be interested in exact answer, but just some degree of probability. Alright? Great. Now, as we all know, probability is always positive and is always less than or equal to 1. And our equation here is y equal to b0 plus b1x. That basically means y here can take any value, including a negative value. But as we just said, probability is always positive. So we apply the exponential function on both the sides of the equation. And that will make it positive, as exponent of this equation will never be negative. Then the second set of condition for probability is it has to be between 0 and 1. And how do we do that? To make it less than 1, we simply divide this further by a number greater than this particular value. So we simply add 1 to the exponent of y and divide the whole equation by the same. And that gives us the probability of success. And if this is the probability of success, then probability of failure would be 1 minus p. And our equation would now look like this. Then if we solve this equation further, our probability of failure will be 1 upon the exponent of y plus 1. Now, in probability, the odd of a particular event occurring is given by its probability of success divided by the probability of failure. And that will be p upon 1 minus p. And when we impute these values, the denominator will cancel each other to give us p upon 1 minus p is equal to exponent of y. Next, we perform the log function on both the sides, which will cancel the exponent, and we get the y. So log of p upon 1 minus p is equal to y, which is nothing but b0 plus b1x. And now, when we plot this on the graph, it looks like this, which represents our data much more accurately than a simple linear straight line. And now we can predict that the data points which are above a particular threshold, and let's say 0.5, will be positive, and those below it as negative. Depending upon your requirement, you may decide to increase the threshold or the cutoff if you want to be more sure about the certainty of an event. So in some cases, you may decide to decrease it, particularly if you do not want any event with certain outcomes to escape from the scrutiny. So for example, if you're trying to predict whether a particular transaction is a fraud or not, by keeping the probability low, we will make sure that the transaction is audited. Because if it skips the audit, the implications could be much severe. The threshold value can be decided based on the business application and what is the cost of finding the false alarms or the false predictions. I hope that clears the concepts behind logistic regression. And in the next lecture, let's start building our first model using logistic regression using Azure ML Designer. So let's go ahead and do it. Thanks for joining me in this one, and see you soon in the next lecture. Have a great time. Hello and welcome. And I'm sure you are excited to build your first model in Azure ML. And for that, let's first try to understand the business problem. It's the same dataset of adult income that we are going to process over here. Here, we have been provided with various data points such as the age of the individual, their working class such as private sector, government, and so on. Then this parameter of final weight simply tells us how many individuals are present in the population with similar characteristics. Then we have the education level, marital status, occupation, relationship, race, sex or gender, number of hours per week they work, their native country, and their current income level. This capital gain or loss is the reported gain or loss due to their investments in instruments such as bonds, stocks, and such. Now, as part of this exercise and based on this information, we need to build a model that will predict whether an individual earns more than 50K or not. So let's now go to the Azure ML Studio and see this data in detail and also analyze it column by column. I have already uploaded the dataset, and I'm going to use the original and the bigger dataset over here. So make sure you drag and drop this dataset on the canvas, and this is also available as the course resources. So let's first visualize and have a look at the data that we are dealing with. And let's now see the profile of this data. And if you see it column by column, you will see that it does not have the missing values, which is good for us. Then these columns of work, class, education, and other string columns have some categorical data. So make a note of that we need to convert them to categorical. Then as we saw earlier, we may have to normalize the numerical data as they are not on the same scale. And by now I'm sure you must have realized that this column of income is the predicted variable for us. So now that we understand the problem as well as the data in brief, and before we start any real work, let's look at the steps required for creating the machine learning pipeline for predicting the income levels. So as part of the first step in the data preparation, we may first need to edit the metadata so that we can convert the string variables to categorical. And if you remember, we didn't have any missing data there. And that's why in this case, we don't need the clean missing data module. Then we split the data into train and test. And here now you must be wondering why we have not normalized the data. Well, the next step is in fact to normalize the data. But as a thumb rule, you should always normalize the train data first and then the test data. Now remember, the training data is what the algorithm is trained on. And the test data is supposed to be the new or the unknown data for the algorithm. So if we normalize the entire data, it does not serve the purpose. So we use the transformation function that gets created during this normalization step and then normalize the test data. Now, once we have the data available, we can then configure the algorithm, which in this case is the logistic regression. We will see what we mean by configuration of the algorithm, and we will also go through various parameters required as part of that configuration. Okay? And once we have the data prepared, once we have configured the algorithm, then of course the next logical step is to train the model using this training data. And in this step, we will be building the equation, calculating the importance of various features or variables within the dataset. And this is then followed by scoring or testing the model using the test data. So in the test data, we already know the answer. We simply use the test to check how the trained model performs or answers the question. And once we have tested the model, we then evaluate how well the model has performed and then provide the evaluation score based on various parameters such as accuracy and few more. As you can see, the steps are pretty logical, and I hope you should not have any problem in understanding the sequence. So let's go ahead and perform these steps in Azure ML Designer. As always, thanks for watching. Welcome back. And as part of our first step, let me search and bring in the edit metadata on the canvas and then make the connections. And now, as we did earlier, click on the edit columns. Then select the column type and the string type of columns. We have done this earlier as well, so you should not face any issue. And save it. Then leave everything else as it is, except making this drop down of categorical to categorical. That's it. Next, let's split the data using the split data module. So search and bring it on the canvas. Great. And let's connect the output of edit metadata to the input of split. Next, let's split it by rows, and let me provide the fraction of split as 0.7. Now, because we have thousands of records here, we can actually use 70% or even higher fraction. So let it be randomized split, and let me give the random seed as 1, 2, 3. Great. And because this is a classification type of problem, as I told you earlier, let's also do the stratified split. And let's provide the stratified column by clicking on this edit column, and then simply type the income over here. There you go. Save it. Great. So we are almost done with bringing in the data, editing the column category, as well as splitting the data into train and test. And let's now normalize the train data first. So search and bring normalized data module. All right. Get it on the canvas. There we go. And as we discussed in the previous lecture, we want to first normalize the training data. So connect the first output node of the split data module to the input of the normalized data module. For now, I'm going ahead a bit quickly as we know what these modules do. But at the same time, I just want to show how the full pipeline gets built with certain steps. And that's why I'm simply repeating them over here. I hope it is okay with you. Next, let me select the transformation method as min-max. And let this parameter be true. And let's select all the numeric columns by clicking on edit columns. Then column type and all the numeric ones. Good. Save it. And right now, we have not executed these steps. So there won't be any output produced. But we know what kind of output will be produced at each of these nodes or ports. And as we discussed earlier, this second node will produce a transformation function that will have all the information that it created while normalizing the training data. And now, as we said, we want to apply the same transformation on the test data. Okay? So how do we do it? And what do we do now? Because even if we want to, we cannot connect this test data directly to this node with transformation function. They always work in top to bottom manner. You cannot take one arrow and connect it to the output. And so what we need to do is we use another module called apply transformation. Let me search it. There you go. And then drag and drop it on the canvas. And good thing is it does not require any parameter, but it has these two input nodes. The first one accepts the transformation function, and the second takes the dataset as an input. And the output is nothing but the transform data produced using this function. So let's connect the normalization transformation function to this first node, and the test data, which is part of this split data module, from this second output node to the second input node of the apply transformation module. I hope you're with me, and you should not have any problem in understanding what we have done here. So just to summarize it, we first brought the dataset, then edited the string columns to categorical, split the data at 70-30 ratio with a stratified column as income. We then normalized the training data and used that normalization function with predetermined values to transform the test data. And for doing that, we use the apply transformation module. Great. And for now, that completes our data preparation steps. And let's now bring in the logistic regression module, train it, and also score and evaluate it. I am so excited to show it to you. But in the interest of time, let's do it in the next few lectures. As always, it's a pleasure to teach you. Welcome back. So after the data preparation, let's now bring in our algorithm and also train it. Now, because we are going to find out whether the income is greater than 50K or not, we are basically classifying the data into two categories or classes. So we then need a two-class logistic regression algorithm. So let me search for logistic, and there you should see this two-class and multi-class logistic regression. And because we have this yes, no or only two classes, drag and drop the two-class module. And as you can see, it does not accept any input. It simply provides an output which can be used to train the algorithm. So those of you who are aware of object-oriented programming, we can say that this module is the class of two-class logistic regression, and the output is nothing but the object of it. And the object is created based on these parameters that we specify. For now, I'm not going to go into the details of each of these parameters. I have a dedicated lecture explaining that, and here I'm going ahead with the default parameters for now. All right? But then the big question is, where and how this object will be used? Well, this object will be used to get itself trained based on the training data. And that training data is coming right from this normalized data module. I hope you are still with me. So we need a module that can take this logistic regression as well as the training data as inputs. Then it trains the algorithm and then provides us with the trained model of that algorithm. And that module is known as, surprisingly, train model. Okay, so let me search for train model, and you will see it right here. Drag and drop it just below the logistic regression, and let me adjust some of these on the canvas so that it's a bit neat and clean. Okay, and now connect the logistic regression to the first input node of the train model, and the training data, which is the trained normalized data, to the second input node. Very nice. And then we need to provide the label column or the predicted column, or you can say that's our y-axis. So once again, what do we want to predict? Well, we want to predict the income level. So click on the edit column and then type income over here. Okay, save it. So the error that we saw earlier is now gone. Leave this parameter of explanations as it is, and we will see that a little later. So now we will have the trained model if we run this. But how do we know how well the model is trained? So we need to give it some exam or some test and then get its score in that test. So now we have this test data normalized as an output of this apply transformation. And the trained model is also here. So basically, we need a module to score the model using these two. And once again, the module to score the model is called very simply, and let me search again, as score model. The nomenclature given by Azure is pretty simple and it is pretty straightforward. So drag and drop it below this train model, and let me make this canvas a bit more visible here. I hope you don't mind me hiding some of these data preparation steps. You already know them. And as you must have noticed, as the number of steps grow, you may want to zoom in and zoom out as per your convenience. But in this training, if I do that, it will be too small. I mean, if I want to show everything as part of this lecture. I hope that's okay. And now connect the trained model from this output node to the first node of this score model. So it goes as an input over here. Then the second input takes the test data as input. So connect the output of this apply transformation, which has the normalized test data, to the second node of this score model. That's it. And we are now ready to run this pipeline. So take a look at all these steps and see how we have progressed so far, right from bringing in the data, normalization, training, all the way up to the model scoring or testing. Now, the only step that is missing here is the evaluation. So up to score, basically the student or our algorithm has simply answered the tests. You can say just the exam has been written. Pass or fail is not known. If our student has passed, then how well it has done or how well this algorithm has done is also not known even after scoring. So for that, the next logical step is the evaluation of the model. But for now, I'm going to run this pipeline right up to this point, and then we will see the evaluation. So let me simply submit the pipeline and make sure the compute target is created. Also create a compute target with at least 2 cores and 8 GB of RAM, because we have thousands of records to process, and it will be done much quicker compared to when you choose the least expensive one. Also make sure that you provide your experiment name and submit again. And this is going to take some time, so go grab a cup of coffee or take a small break if you want to, but do not go very far away for a long time, because for now, I'm going to end this lecture here and I will be back with another interesting module called as Evaluate Model. As always, it's a pleasure to teach you. Thanks for watching and keep a tab on this experiment run. Welcome back. So this pipeline has completed successfully, and if you have been doing it along with me, congratulations on completing your first pipeline on Azure ML. Now let's see the output of this score model. So right click and preview the score dataset. And now it has got these 2 additional columns, and that's why you see the columns as 16 instead of 14. Scroll to the right and you will see the scored labels and scored probabilities added right over here. So what does that mean? Well, this is the test data that was provided to the trained model for scoring. And what has happened here is our trained model took this test data, and based on the training provided, it started assigning the probabilities to each of these records. And then based on whether the probability was greater than 0.5 or not, it assigned a label of either less than equal to 50K or greater than 50K. So as you can see here, it assigned the probability of 0.38 to this record, and that's why it is labeled as less than 50K. And you will see that for all these records. And now if you go down, you will see that this record has a probability of more than 0.5, and that's why it is labeled as greater than 50K. Alright? Now, our model has done that based on just the probability. It didn't know what the actual label was, and that's why some of these labels could be incorrect. So let me check one such record where we have the inaccurate result. Okay, there you go. So here, even though the actual label is less than 50K, our model has scored a probability of more than 0.5, and that's why it labeled it as greater than 50K. Now, this is an error and not an accurate scoring. So basically, there will be some records which are labeled correctly, and there are some which are labeled incorrectly. So the next question is, how do we find out that particular summary, and how do we evaluate this model for its accuracy? Because going through it one by one is surely not a correct way of doing it. So let me close this. And for evaluating the model, we use another module which simply goes by the same name. There you go, drag and drop it here. And it does not need any parameter. But it has these two nodes which take the score datasets as input. So basically, if we are creating multiple models with different algorithms, we can compare them here by providing them as input to this module. And just hold on to your thoughts for now. We will do that comparison a little later. But for now, I'm going to connect the output of this score model module, which has the scored dataset, to the input of the evaluate model. And let me submit this again. And this time, it won't execute all these steps. So it should be done within a minute or so. So while it runs, let me end this lecture here, and let's discuss the result of evaluate model in the next lecture. Thanks for watching. Welcome back, and now let's preview the evaluation results. So our output appears something like this, with all these charts of ROC curve and these two other curves. We also see these metrics of accuracy, precision, recall, along with these score bins, etc. So what does that mean, and how should we interpret these results? For a moment, let's go back to the output of score model and preview that data. Now, as you can see, in our test dataset, the income column has actual data. So if we assume that less than 50K is a negative value and greater than 50K is a positive value, then we can call the values in this column as actual positives and actual negatives. All right. And then after we ran the score model, we had predicted results as part of this column of scored labels. These also were positives as well as negatives. And in most of the cases, they match, but in some cases, the actual and the predicted results are different. All right. Now, in order to understand what's going on here, let's try to plot the positives and negatives in the actual versus the predicted matrix. So we have actual positives and negatives, as well as the predicted positives and negatives. Now, all those positive cases where the actual results and predicted results match, we call them true positives. And those results where the actual and the predicted both were negative, we call them as true negative. All right? Then the results where we predicted them as a positive, but in reality, it was a negative result. That basically means we falsely categorize them as positive. Okay? So that's why we call these as false positives or falsely predicted as positives. And similarly, we may have some results where they were actually positives, but we predicted them as negatives. And these are called as falsely predicted negatives or false negatives. So get this terminology of true and false and positive and negative absolutely correct. Then let's try to understand the confusion matrix and some other characteristics using an example. So in this graph, let's say all the circles are positive results and all the triangles are negative results. And our model predicted these results as positives and these ones as negative results. Then in that case, our true positives are all the circles within the blue line, which is 8 in number. And our false positives will be this one triangle that was actually a negative, but we falsely predicted it as positive. Okay? And similarly, we can also calculate the false negatives and true negatives. So then we also sum it up across predicted and actual results. Great. And I hope by now you are clear how this confusion matrix has been constructed. And based on this confusion matrix, let's now try to learn how the characteristics or the metrics of accuracy, precision, recall, and F1 score are computed. So accuracy is nothing but the proportions of total number of correct results. Okay? So the correct results are all the true results. And true can be both the true positive and the true negative. So what we are saying is accuracy is nothing but true positive plus true negative divided by the total number of results. Okay, so in this case, we have 8 true positives and 4 true negatives, and the total number of observations are 15. So it is 8 plus 4 divided by 15, and that's why the accuracy here would be 0.8 or 80%. And similarly, precision is proportion of correct positive results out of all the predicted positive results, which is nothing but the true positive, which are the correct positive results, divided by all the predicted positives. So here we have predicted 8 true positives, and total predicted positive results are 9. So it is 8 divided by 9, and hence the precision is 0.889 or 88.9%. Then the next result is of recall. Now recall is a proportion of actual positive cases that the model predicted correctly. So out of total actual positive cases, how many are predicted correctly? So that is nothing but the true positives, which are the correctly predicted results, divided by the total actual positive results. And in this case, we have total 10 results as positives, but we could only predict 8 correct and 2 as false positives. And that's why in this case, the recall is 8 divided by 10. That is 0.8 or 80%. I hope you are following me. And I would suggest, in case this is a bit confusing, go through this lecture again and maybe even try to do this in an Excel. Now, let's consider the F1 score, which may require a bit more explanation. So F1 score is nothing but the weighted average or the harmonic mean of precision and recall. Now, when measuring how well you are doing, it's often very useful to have a single number to describe your performance. I mean, we could define that number to be the mean or the average of your precision and your recall. And this is exactly what the F1 score is. But it is not the normal mean or the normal average. The formula for that is, I've given it over here. And the value for that, when you substitute these values, will be 0.84. Now, the only reason why we use the harmonic mean is because we are taking the average of ratios. Okay, so the recall, precision, these are the derived ratios, and we are taking the average of those ratios. And in such cases, the harmonic mean is more appropriate than the arithmetic mean. And let me explain that by an example. I'm sure you now understand that I love to explain things using examples. And in case you already know, you can skip it or stay with me for a revision of the concept. So let's say our model has identified these 6 positive results. And that's why our confusion matrix would look something like this. Now, after applying the formulas, our precision is 100% because we only identified true positives. We didn't identify a single false positive. And recall is only 60%. Now, if we want to compare it with the previous example based on simple average of precision and recall, it may lead to false interpretation. So we may end up saying that both the models are more or less okay, or they're very close to each other. Whereas when we calculate the F1 score based on the formula that we saw, that would give us a better value of predicting which model is performing better in comparison to precision and recall. Alright? And now that brings us to the last topic in this lecture, that is AUC ROC, or area under the ROC curve. And it's nothing but plotting the true positive rate on y-axis and the false positive rate on the x-axis. The area under this curve provides us a single number, and using that number we can compare models of various types. I know it is not very self-explanatory, so let's understand it again with an example. And before that, let me take you back to the history and then see why it is called as ROC. You can pause the video here if you want to, and then read why it is called as ROC. But in the interest of time, please allow me to explain the ROC curve in the next lecture. As always, thanks for watching. Welcome back, and let's now try to understand how the AUC has been plotted so that you appreciate its value in comparing different models. And for this purpose, I have plotted our results of adult income in an Excel. So I have this Excel that you can download and try for your model, and you can create your own ROC curve as well. You just need to make sure that you identify the true positives and true negatives correctly. Basically, in this Excel, the predicted and the actual results are on different axes. Okay, so let me open the Excel and the browser side by side so that you understand what's going on here. So what I have done is change the value of this threshold starting from 0.05 all the way until 0.9. And you can do that by simply dragging this slider over here on the browser. All right. And then I captured the true positives, false negatives, false positives, and true negatives based on these different thresholds. I hope that is clear. Now, as you can see here in this matrix, I have calculated the true positive rate as TPR and false positive rate as FPR. So true positive rate is nothing but the true positives divided by the total actual positives. And false positive rate is nothing but false positives divided by total actual negatives. Okay? And I simply got these 12 data points for false positive rates and true positive rates for a given threshold. And then when I plot them, this is what I see. And now you can very well compare this with the actual plot that you see on the browser. Then again, you may ask, what is the benefit of it? Well, an ROC curve visualizes all possible threshold. So let's say the business comes to you and asks, if I want to capture 90% of the positive predictions, how many wrong or false positives will I get? And that can be answered very simply by going to the chart and see the false positive rate at the TPR of 0.9. And you will know that you will have a false positives of almost 28 to 29%. So then, based on this particular chart, you can say that for a better model, this particular line will go almost straight. So what that means is, even if you achieve a TPR or a true positive rate of more than 90% or even 95%, you would have a very less false positive rate. And a model which has 100% accuracy, this will be almost a straight line. And in that case, the area under the curve will be 1. So the area under the curve, irrespective of what kind of algorithm you have used, can be used as one of the measures to identify how good the model is. Okay? And then in case you're wondering how to set the threshold, well, it's more of a business decision. So let's say your model is used to predict whether a given credit card transaction is a fraud or not. The business decision might be to set the threshold very low. Now, a very low threshold can result in a lot of false positives. And that might be considered acceptable because it would maximize the true positive rate, and that means it will minimize the number of actual fraud which were earlier not flagged. At the same time, this also means that there will be too many transactions for auditing, and it could become a manpower issue as well. And even the customers may get dissatisfied if each and every transaction or a very high number of transactions are held back. So there is always a trade-off, and that's why it's always better to let the business take that call while you as a data scientist provide all the possible scenarios. All right? Great. We have now covered a lot of theory, and I have tried to make it as easy as possible so that you can understand all these concepts at a very basic and in the simplest possible manner. And with that, we have come to the end of this lecture on understanding the results of a model. In the next one, let's understand the parameters of logistic regression, which we haven't seen in detail. So see you in the next class, and have a great time. Welcome back. And in the last lecture, we built our model using two-class logistic regression and ran it successfully with a very good accuracy. And we saw some parameters there that our untrained model expected. In fact, every algorithm has a set of input parameters, and they are also known as hyperparameters. Hyperparameters are like knobs that the data scientists use to get the optimum results. And for now, let's go through those parameters one by one. So the first is the trainer mode, and by setting this create trainer mode option, you can specify how you want the model to be trained. The single parameter is when you know what is the best combination of various parameters, but that usually does not happen. You may want to figure out the best possible combination, and that is when the trainer mode of multiple parameters helps us. And if you select this as an option, as you can see, you will be able to input multiple values and even the range. And when we are using this option, you should use the tune model hyperparameter. And what it basically does is it creates various combinations of these values and then runs the model multiple times with each set and provides us the best result. And if you're not getting everything 100% right now, please do not worry, as I will be adding a tune model hyperparameters section where we will cover that in much greater details. Then next parameter is optimization tolerance, and that is a big word. And as per Microsoft, it's a threshold value to stop the model iterations. So what does that mean? Well, as we have seen, this is the formula for the logistic regression. And we say that all the values above 50% probability are positive and below that are negative. But how do we arrive at the best possible values of B0 and B1? And that is so that we have minimum number of errors. Because if we arbitrarily give some values to B0 and B1, we may get a plot like this. So we iterate over these values and come up with multiple options such that the number of errors are minimum. And we may assign a cost function which essentially comes up with some sort of cost, and our aim would be to minimize that cost. Then in the second iteration, we may get a curve like this. And we then go on and try to minimize the errors, and our curve will start converging to the best possible result. But that creates another problem of when do we start iterating? Because it will never get an absolute minimum value. So what we do is we provide a threshold called optimization threshold. And this threshold tells the model to stop when these curves are not optimizing beyond a particular value. Okay, and that value is the optimization tolerance. I hope it explains this particular parameter. Now, let's see what is this L2 regularization. And before we understand that, it is very important to know what is regularization in the context of overfitting. So let's try to understand that using regression. So let's say we have a data set with points plotted as shown over here. And a straight line equation can clearly show that this is underfitting because most of the points are away from the line. It won't do any good for predicting any new data point. And similarly, in this equation, if we try to create an equation that makes the line pass through almost every data point, that will also be a problem because it won't be good to predict a new data point. And this is called as the problem of overfitting. So what we need here is a trend that can predict with optimum accuracy, such as this one. So can you guess what is causing this overfitting? Well, it is these coefficients whose large values can have significant impact on the outcome. So the B2 and other coefficients, or weights as they are called, are the reasons for the model to overfit. And what if we can significantly reduce or even in certain cases eliminate them by making them zero? Well, that's what L1 and L2 regularization tries to achieve. What they do is they penalize the values of these coefficients and also minimize the error between predicted and actual observations. So L2 regularization is performed by ridge regression, which we will see later on in greater details. And it strings all the coefficients by the same proportions. But it does not eliminate any of these. Whereas the L1 regularization, or it is also known as lasso regression, it will shrink some of the coefficients to 0. So in this example, if we use higher values for L1, it might even make B2 as 0, and that's why it will prevent the overfitting. So basically, it is also doing some sort of variable selection. And because we will have more relevant features or variables in our equation, we can actually choose those. Great. And as we have seen, both L1 and L2 regularization prevents overfitting by shrinking, or we can say imposing a penalty on the coefficients. With L2, you tend to end up with many small weights or small coefficients, whereas with L1, you tend to end up with larger weights or larger coefficients but more zeros. And then you should also note that if you specify large L1 and L2, that could lead to underfitting, whereas very small values could lead to overfitting. I'm going to include a separate lecture explaining the ridge and lasso regression if time permits. And we will also see some examples and how these things actually penalizes some of these coefficients. For now, it concludes the lecture on two-class logistic regression parameters. And as a practice, I suggest you perform the same model training using different parameters. And then see what kind of impact it will have on the result, particularly on the accuracy and the AUC. For now, I'm going to end it here. And as always, thank you so much for watching. Hello and welcome. And now in this section, let's learn and build our model using decision tree. And let's also understand what exactly is the decision tree. Well, at a high level, once again, it is one of the supervised learning method. And it is a decision support tool that uses a tree-like graph or a model of decisions. And of course, it also has their possible consequences. And this particular tree will help us in making the predictions. Then it also has various variations such as boosted decision tree, random forest, and so on. And we will go through them in subsequent lectures. Then decision trees and its variations are also used for categorical as well as the continuous types of variables. Alright, I think this is good enough for an overview. And let's now see how exactly it works. Well, let's try to understand that using an example. So let's say you are trying to predict whether the loan application of a customer will be approved or not. And let's say if you only have one parameter, such as income level, and based on that, you need to predict whether the loan will be approved or not, it would be very easy. But you see variations there as well. Not all applications with medium income level have been approved. So let's bring in another feature and let's call it credit score and see if that helps. Well, here also we see variations in the approval process. The income level and credit score may have a cumulative impact on the overall approvals, but not individually. So what if we bring in another variable and let's call it employment type and then keep adding more features one by one. And then it will be very difficult to simply analyze the loan applications for so many variables or so many features. So if we assume this is the historic data and a new record comes, will we be able to predict it? Well, it will take a huge amount of time to figure it out. So how can we answer that efficiently using machines? Well, that's where something like a decision tree helps us. So let's try to build a decision tree for this particular data. So let's start with the income level. And let's ask questions about every parameter. So depending upon the income level, will the loan be approved or not? So we have three income levels here, high, low, and medium. So we divide our observations according to the income level first. And as you can see, all the applications with high income levels were approved. That was pretty easy. And the goal of the decision tree in classification is always try to come up with the pure subset. And a pure subset is something where you have only one outcome. And in this case, we have all observations with only one outcome, and that is yes. So we do not split it further. And similarly, for low income, we see that there is only one outcome. And that's why we say we have reached a pure subset here as well, and we do not split it any further. But for the medium income level, we see that there are some approved and some not approved applications. And we cannot say convincingly what? That this is a pure subset. And because of that, we decide to split it further. So let's split it on the credit score. And we have two values of credit score here, low and high. So let's see how the observations look like when we split them on the credit score. And as you can see, the applications with medium income level and high credit score always get approved. So once again, we have a pure subset here. But with low credit score and medium income level, we still have not reached pure subset. So we decide to split it further. And let's now split it on the third variable, that is employment type. And we have two values for the employment type, that is salaried and self-employed. And now when we split the data set on these two, we do get the pure subsets. So whenever a new application comes, we can traverse through these nodes and then predict whether the loan will be approved or not. This is precisely how decision trees work. And as you can see, it looks like an inverted tree, and that's why the name is a decision tree. And let's now get ourselves familiar with some of the common terms that are used for the decision tree. And many of these terms will actually be parameters of the algorithms, and they also decide the accuracy of our model. So please pay very close attention to it. Alright? So in the decision tree, there is a root node, or that is the first node that represents the entire sample dataset. And then the process of forming various decision nodes below the root node is called as splitting. So when a subnode splits into further subnodes, then it is called as a decision node. And when we cannot or do not want to split a decision node any further, it is called as the leaf or the terminal node of the decision tree. Then this subsection of this entire tree that has one or more decision nodes and two or more leaves is called as a branch or the subtree. I hope that explains the intuition behind what is a decision tree. And in the next lecture, we will try to understand some additional concepts of bagging and boosting decision trees before we start creating our machine learning models. As always, thank you so much for joining me here. Have fun. Hello and welcome. And now that we know what is decision tree, how it works, as well as various terms and definition, let's see some of the improvements in the original concepts of decision trees. So in this lecture, we are going to cover what is known as ensemble learning, and it is a very powerful way to improve the performance of your decision tree model. So let's try to understand ensemble learning using a day-to-day example. So let's say you have decided to purchase a house. You have made the visit, and the seller has also given you a price. But before you make a final decision, some doubts and questions come up in your mind, such as, is this price fair? Will I get a good appreciation in case you are thinking of selling it at some point in future? Then is this the right neighborhood for you and your family? I mean, another could be, is the location appropriate? What about the construction quality? How can you be sure about it? And many such questions will come up. So now you have a real dilemma because you are not an expert in many of these things. So what do? Well, you go and ask the experts or those with the knowledge to get an answer. You may ask a broker or visit a real estate portal to check the fair price and price appreciation. You may even ask a friend or colleague who stays nearby or stayed in the neighborhood in the past. For construction quality, you may even get an inspection done by an architect for quality checks and structural defects. As you can see, there is no one single expert here that can answer all the questions. But from multiple experts, you got these questions answered. And maybe not all the questions would be to your satisfaction. So what do? Well, either you go by the majority or you can take the weighted average in terms of which one is more important for you, and then accordingly you will take a call. Ensemble learning is used in exact same way. So what is it anyway? Well, as we know by now that all algorithms have some form of errors, and our aim is to minimize the errors as much as possible. We also know that collective wisdom is higher than the individual intelligence. For example, we many times have a panel of judges on many crucial judgments rather than one best judge in the country. In ensemble learning, we generate a group of base learners and combine the results to get higher accuracy. Now, each of these base learners can use different parameters, sequence, or even training sets. Great. And finally, there are two major ensemble learning methods known as bagging and boosting. But in the interest of time, let me explain that in the next lecture. As always, thank you so much for joining me here. Welcome back. So now that we know what's ensemble learning, let's have a look at what do we mean by bagging. In bagging, we build various models in parallel using bag of data. And that is nothing but splitting the data and creating different bags on which each of the base learner is modeled. Then all the models vote to give final prediction. So as you can see in this particular case, we have these 4 base learners or models which predict an outcome. Here, for a particular observation, we have 3 Ys and 1 N. And that's why our final prediction by majority will be a Y. I hope that is clear about what is bagging. It is not that difficult to understand once you get the intuition behind it of creating different samples and then taking a collective decision. Random forest algorithm is an example of ensemble learning method. Many times it is also called as decision forest. Now let me touch base upon another ensemble learning method of boosting. Now in boosting type of ensemble learning, we train the decision tree in a sequence. But the algorithm learns from the previous tree by focusing on incorrect observations. And we then build a new model with higher weight for incorrect observations from the previous sequence. I know it could be difficult to understand these terms without a proper visualization. So let's try to understand that with an example and some visualization as well. So let's say we have a dataset that has observations spread in this fashion. And there are two classes in this dataset represented by the triangles and the circles. So just for argument's sake, hypothetically speaking, our first learner may create a decision boundary somewhere over here. Now, as part of this decision boundary, it has identified these four triangles and these four circles correctly. But it made a mistake in identifying these two circles and these two triangles. So these mistakes serve as the learning for us, and we would like to correct them in the next sequence of learning. So in the next sequence, we increase the weight for these four observations and create a new decision boundary to identify these observations. So now we have these two observations identified correctly, but not the two circles. So we go for another sequence and create another decision boundary that will identify these two observations correctly. Alright? So we have run the decision tree for 3 sequences and then tried to improvise it in every sequence. And now is the time to combine or ensemble what we learned. And there we have our final decision tree that can identify all the triangles and the circles correctly. And this is nothing but boosting. Okay? And that also brings us to the end of this lecture on ensemble learning. So by now we covered what is ensemble learning and what do we mean by bagging, which is nothing but collective intelligence of different models. Whereas boosting relies on sequential learning. Great. And in the next lecture, let's build a classification model using decision tree. As always, it's a pleasure to teach you. Thank you so much for joining me here. Have a great time. Welcome back. And now let's see how to use the decision tree for classification. So we have this logistic regression model already built. And what I'm going to do is use this same data as well as all the data processing steps. And the reason I'm doing it is so that you understand how to evaluate more than one model at a time. You will also see how easy it becomes to use different models using Azure ML Designer. So let me simply search for the decision tree. And then out of these, we are interested in the 2-class boosted decision tree. So drag and drop it on the canvas. And as you will see, it requires some of these parameters. So let's go through them one by one. So create trainer mode is same as what we saw for logistic regression. For now, let me keep it as a single parameter. And then comes the maximum number of leaves per tree. Now, if you remember from the previous lectures, we said that the terminal nodes which do not get split are nothing but the leaves. So this parameter defines the maximum number of leaves or terminal nodes beyond which we will not split the node. Okay? Then the minimum number of samples per leaf tells us that we should not split any node if we are not going to have less than the minimum number of records in the leaves that will get created. So if we specify 10 over here, then any node with 19 or less number of records will not be split. Because if we split it and let's say it may go evenly or otherwise, it may result in one node with less than 10 records. Great. Then learning rate is nothing but the step that our algorithm need to take in order to reach the minimum error. For now, I'm going to keep it as it is and park it for now. You will get this learning rate once we go through the gradient descent lecture. Then the next parameter specifies the maximum number of trees that we need to build or we want our algorithm to build. I'm going to change it to 500 for now. We have quite a few records over here. And random seed can be any random number. So you can give 0, 1, 2, 3, 4, 5, 6, whatever. Great. Then next, we need to train our boosted decision tree. So let's bring in the train model module. Or you can simply copy and paste this particular one. Or you can search and get it over here. Only thing that you need to make sure is the label column is income. Now, as we know, this requires the algorithm as well as the training data. And we already have the training data. It's coming from this first node of the normalized data. So connect that data to the train model. Then we are going to use the same training data so that we can compare the two models side by side. Okay. Then let's connect this decision tree to the train model. Now, beyond two models, this can become a bit messy with all these arrows going all over the screen. So if you have a bigger screen, it makes much more sense to add a complex pipeline. Otherwise, just zoom them out. Okay. Then next, let's score the train model. So let me copy and paste this score model module. And here, make sure the append score column parameter is true. Once again, connect the same test data to the score model and the train model from this module to the first node of score model. Great. And finally, if we want to compare the two models, we can connect the scored dataset of the decision tree to this evaluate model. So do that as well. Great. And as you can see, once our data preparation steps are done, adding multiple algorithms is very easy. We can even compare them side by side. Now, if you want to add multiple algorithms and compare them, you can have multiple evaluate model as well. Just one thing that you need to remember, that it has limitations of comparing two models at a time. All right. So now let's go ahead and submit this pipeline. Make sure that the compute is created. And for now, I'm simply going to use the same experiments as before and then submit it. So let it run for a few minutes and I will be back in the next lecture where we will discuss the result as well as the comparison. As always, thanks for joining me here. Welcome back. So our experiment has run successfully and now let's see the result of it. So if you check the output of the score model and preview the scored dataset, the output looks exactly similar. So we have the 16 columns with the scored labels and scored probabilities added at the end. The scored label and the values of scored probabilities could be different than the logistic regression, but the format of the scored dataset is always the same. I mean for the classification. Okay, so let me close this and let's now see the output or the evaluation results of the evaluate model. And as you can see, it has these two tabs for left port and the right port. It also shows these overlapping curves for the two trained models. Now, as we know, the left port shows the evaluation of logistic regression and the right one is for decision tree. We have seen this accuracy and other metrics for logistic regression. So simply click on the right port tab and there we have the results of the decision tree. So as you can see, the accuracy of the boosted decision tree for the parameters that we provided is better than the logistic regression. So it was 0.85 for logistic, whereas for decision tree, it is 0.87. So almost 2% higher than the logistic regression. Apart from that, we also have a better AUC of 0.921 compared to 0.899 for the logistic. Great. So in this scenario, we can fairly say that the boosted decision tree has performed better than the logistic regression. But these results are based on the parameters that we have provided. And close it and come back to the canvas. And what that means is if we change these parameters for decision tree as well as logistic regression, we may get different results. And who knows, with certain changes in its parameters, even logistic regression can perform better. And we will see how to get those optimum parameters when we discuss the hyperparameter tuning. But for now, we have come to the end of this lecture on decision tree. And I hope now you know what is decision tree along with its variants and how to use this boosted decision tree module as well as compare two different models. As always, it's a pleasure to teach you. Thanks for watching.